1 million miles from Earth, a telescope floats in the cold darkness of space, capturing light that left its source when the universe was still a cosmic infant. That ancient light has been traveling for more than 13 billion years. What it reveals is shattering everything scientists thought they understood about cosmic evolution. Galaxies that should not exist, black holes too massive for the time they appeared, stars thousands of times heavier than our sun that burned and died before most of the universe had formed. The James Webb Space Telescope has looked deep into the unknown, and what it found is not just surprising, it is forcing physicists to rewrite the fundamental laws governing how the cosmos came to be. If you enjoy these journeys and want to keep exploring the cosmos with us, please like and subscribe. It helps more than you know. Now, let's begin. Every telescope is a time machine. This is not poetry or metaphor, but fundamental physics. Light travels at 670 million miles per hour, the fastest speed anything can achieve in our universe. Yet cosmic distances are so immense that even light requires billions of years to cross them. When you observe an object 10 billion light years away, you see it as it existed 10 billion years ago. The photons entering your telescope began their journey when the universe looked completely different from today. Point sufficiently powerful instruments at the distant cosmos, and you witness ancient history unfolding in real time. This time travel capability emerges from the finite speed of light, combined with the staggering vastness of cosmic space. Nothing can outrun a photon racing through the vacuum, yet the distances separating celestial objects dwarf any scale humans evolved to comprehend. The nearest star beyond our Sun lies over 4 light-years distant. Light leaving that stellar neighbour tonight will not reach Earth until 4 years have passed. The nearest major galaxy sits 2.5 million light-years away. Photons from Andromeda began their journey when early human ancestors were learning to fashion stone tools. Every glance at the night sky is a glance backward through time. The deeper you look into space, the further back in history you peer. Previous telescopes exploited this principle to observe ancient cosmic epochs. The Hubble Space Telescope studied galaxies existing when the universe was roughly 1 billion years old. Ground-based observatories pushed slightly further, using specialized techniques, but a fundamental barrier blocked access to the earliest cosmic times. The most ancient light has been stretched by cosmic expansion, shifting from visible wavelengths into infrared frequencies that Earth's atmosphere absorbs. Water vapor and carbon dioxide in our air block most infrared radiation from reaching ground-based detectors. Observing the universe's infancy required an infrared telescope stationed beyond our planet's obscuring blanket of air. Webb was built specifically to overcome this barrier. Its 21-foot gold-plated mirror collects infrared photons with unprecedented sensitivity. The gold coating optimizes reflectivity at infrared wavelengths, where the most ancient light now resides. Its position at Lagrange 2, nearly 1 million miles from Earth, keeps the telescope cold enough to detect the faintest thermal whispers from the ancient cosmos. A tennis court-sized sunshield blocks solar radiation, allowing Webb's instruments to cool to temperatures approaching absolute zero. At these frigid conditions, the telescope's own thermal emission drops low enough that it does not overwhelm the incredibly faint signals arriving from the distant universe. 4 sophisticated instruments analyze incoming light across infrared wavelengths, inaccessible to any previous observatory. The near-infrared camera captures images at wavelengths slightly longer than visible light. The near-infrared spectrograph separates light into component wavelengths, revealing chemical compositions and physical conditions in distant objects. The mid-infrared instrument extends coverage to even longer wavelengths, where warm dust and cool gas emit radiation. The fine guidance sensor keeps the telescope precisely pointed, while also conducting scientific observations. Together, these instruments transform Webb into the most powerful astronomical observatory ever deployed. When Webb opened its eyes to the universe, It could see further back in time than any instrument humanity had ever constructed. The telescope's sensitivity exceeded Hubble's by factors of 100 at certain wavelengths. Objects invisible to every previous observatory suddenly became detectable. The cosmic frontier expanded dramatically, revealing epochs when the universe was transitioning from primordial simplicity to the structured complexity we observe today. The telescope's first deep observations targeted seemingly empty patches of sky. These regions contain no bright foreground stars or nearby galaxies that might overwhelm faint background sources. Webb stared at these blank fields for hours, accumulating photons from the most distant objects in the observable universe. Each additional hour of exposure revealed fainter sources, pushing the detection threshold toward ever more distant cosmic epochs. When researchers processed the resulting images, they found themselves staring at cosmic eras no human technology had ever witnessed. In May 2024, an international collaboration confirmed the most distant galaxy ever observed, designated Jade's GSZ 14-0. This ancient structure emitted its light when the universe was merely 290 million years old. The cosmos is currently 13.8 billion years old. This galaxy existed when universal time had completed barely 2% of its present span. To grasp how remarkable this detection is, consider that the universe needed to expand for over 13 billion years before those ancient photons finally reached Webb's mirror. The light travelled across nearly the entire observable universe, stretched by cosmic expansion until its wavelength increased by a factor of 15. Finding a fully formed galaxy at this epoch was like discovering a mature oak tree in a forest that had been growing for only 2 weeks. Standard cosmological models predicted that structures forming this early should be small, dim, and primitive. The universe had not existed long enough for gravity to assemble vast matter concentrations. Primordial gas needed time to collapse into dense clouds. Those clouds needed time to fragment and ignite into stars. Stars needed time to burn through their nuclear fuel, explode as supernovae, and seed space with heavy elements enabling subsequent stellar generations. Everything theoretical models predicted about early galaxy formation suggested gradual development from humble origins. The galaxy's observed properties compounded the mystery. Jade's GSZ 14-0 spans more than 1,600 light-years and shines with luminosity, requiring billions of cooperating stars. This was not a small, primitive clump struggling to assemble its first stellar generation. This was a substantial structure already churning out stars at rates exceeding modern galaxies by enormous factors. Spectroscopic analysis confirmed that starlight dominated the galaxy's emission rather than radiation, from a central black hole consuming surrounding material. The structure had built its stellar population through processes far more rapid than any theoretical model had anticipated. The discovery carried an additional disturbing implication. Researchers calculated that they could have detected Jade's GSZ 14-0, even if it were 10 times fainter. This detection threshold suggests that similarly luminous galaxies likely exist at even earlier cosmic times, perhaps within the first 200 million years following the Big Bang. The universe apparently began constructing massive galaxies almost immediately after physical conditions permitted structure formation. Whatever processes drove this rapid assembly operated with efficiency that theorists never predicted. But Jade's GSZ 14-0 was not an isolated anomaly. Webb's surveys of the early universe revealed entire populations of objects that defied theoretical expectations. A class of compact, distant sources earned the nickname Little Red Dots from astronomers puzzled by their properties. These objects appear red because cosmic expansion has severely stretched their light toward longer wavelengths. They are compact, meaning they occupy small angular sizes on the sky despite their enormous luminosities. And they exist in numbers that vastly exceed model predictions. Where theories suggested finding perhaps a handful of such objects, Webb detected hundreds scattered across survey fields. spectroscopic observations revealed that many little red dots contain actively growing supermassive black holes surrounded by substantial dust concentrations. Their spectra show signatures of gas heated to extreme temperatures by gravitational compression near central mass concentrations. Emission lines from highly ionized atoms indicate conditions found only in the immediate vicinity of accreting black holes. The objects represent a population of early massive black holes that standard theory never anticipated finding in such abundance at such early cosmic times. The implications of these discoveries for black hole formation and growth would prove revolutionary, challenging fundamental assumptions about how these cosmic monsters come to exist. The abundance of little red dots creates profound theoretical challenges. Standard models predicted that massive black holes and their host galaxies should grow together over cosmic time, maintaining a consistent relationship between black hole mass and galactic mass. Observations of nearby galaxies confirmed this relationship. Bigger galaxies host bigger black holes in predictable proportions. Little red dots violate this relationship dramatically. They contain black holes far more massive than their small host galaxies should support according to established scaling relations. The early universe apparently operated under different rules than the cosmos we observe in our local neighborhood today. Amid these puzzling discoveries, Webb captured one ancient galaxy in a more comprehensible state. The object, nicknamed Firefly Sparkle, exists approximately 600 million years after the Big Bang and displays characteristics remarkably similar to what our Milky Way might have resembled at the same cosmic age. Unlike the inexplicably massive structures that challenged theoretical frameworks, Firefly Sparkle shows what normal early galaxy assembly actually looks like when proceeding according to expectations. The discovery relied on a cosmic magnifying glass provided by nature itself. A massive foreground galaxy cluster lies between Earth and Firefly Sparkle. The cluster contains hundreds of galaxies bound together by mutual gravitational attraction. This enormous mass concentration warps space-time severely enough to act as a natural lens, bending and magnifying light from background objects. Rays of light that would normally spread apart as they travel toward Earth instead converge, enhancing the apparent brightness of anything lying behind the cluster. This gravitational lensing enhanced Firefly Sparkle's apparent brightness sufficiently for Webb to resolve internal structure that would otherwise blur into a featureless smudge. Webb distinguished 10 separate star clusters within this single ancient galaxy. Each cluster occupies a different evolutionary stage. Some burn blue-white with recently formed hot stars whose surfaces exceed 20,000 degrees. Others glow red, with older, cooler stellar populations that have been shining for millions of years. The galaxy caught in mid-assembly shows staggered star formation, rather than a single explosive burst. Different regions ignited at different times, building the galaxy piece by piece over cosmic timescales measured in millions of years. 2 companion galaxies orbit within 42,000 light-years of Firefly Sparkle. These neighbors will eventually merge with the primary structure, contributing their stars and gas to the growing system. Gravitational interactions between the merging components trigger additional star formation episodes as gas clouds compress and collapse. This merger-driven growth matches theoretical predictions for how galaxies assembled in the early universe. Firefly Sparkle represents the expected process operating as theories suggested. The massive, fully formed galaxies discovered elsewhere represent something entirely different, requiring additional explanation. Webb found another peculiar object that occupied a transitional evolutionary state, unlike anything previously observed. Galaxy GSND G9422 exists approximately 1 billion years after the Big Bang. When researchers analyzed its spectrum expecting typical stellar signatures, they discovered an unprecedented phenomenon. The galaxy's gas was outshining its stars. Normally, stellar emission dominates galactic light output, while gas contributes secondary spectral features visible only through careful analysis. In this strange system, nebular emission from superheated gas overwhelmed stellar contributions by substantial factors. The stars were practically invisible compared to the glowing gas surrounding them. This bizarre spectral signature matches theoretical predictions for environments surrounding the universe's very first generation of stars. These primordial objects, designated Population 3 stars, formed from pure hydrogen and helium without any heavy element enrichment from previous stellar generations. Theory predicted that Population 3 stars would achieve enormous masses and extreme surface temperatures far exceeding any stars forming today. These stellar monsters would heat surrounding gas to conditions unlike anything in the modern universe, producing exactly the gas-dominated spectra Webb observed. Galaxy GSNDG 9422 does not contain Population 3 stars directly because its spectrum reveals chemical complexity, indicating previous stellar generations had already enriched the gas with heavy elements. But its stellar population appears to represent immediate successors, a transitional phase between primordial stellar generations and the chemically enriched populations dominating modern galaxies. The universe was transitioning from its first stars to something more familiar, and Webb captured evidence of this transformation preserved across billions of years. The discovery suggests that transitions between stellar population types left observable signatures persisting for hundreds of millions of years after the transition occurred. The universe's first stars burned intensely but briefly, perhaps only a few million years each. When they died, they seeded space with heavy elements and established conditions for subsequent stellar generations. Galaxy GSNDG 9422 preserves evidence of this transitional epoch, capturing cosmic adolescence between primordial simplicity and modern chemical complexity. We are witnessing the universe growing up. Another discovery challenged understanding of how light escaped the early universe entirely. Webb detected bright hydrogen emission from galaxy JADESGSZ 131, which existed merely 330 million years after the Big Bang. This emission should have been impossible to observe based on standard models of cosmic evolution. During this cosmic epoch, the universe was permeated by a thick fog of neutral hydrogen atoms that had formed when the cosmos cooled sufficiently for protons and electrons to combine. Ultraviolet radiation from young galaxies should have been absorbed by this fog long before photons could travel the billions of light years separating ancient sources from modern telescopes. The standard model of cosmic reionization describes how ultraviolet radiation from early stars gradually ionized the neutral hydrogen fog, stripping electrons from atoms and making the universe transparent over several 100 million years. This process created expanding bubbles of ionized gas around young galaxies that eventually merged to clear the cosmic fog entirely. But this process should not have progressed sufficiently at 330 million years to permit bright hydrogen emission escape from JADESGSZ 131. The fog should still have been too thick. Researchers proposed several explanations for how this light pierced the supposedly opaque early universe. Perhaps this particular galaxy resided within an unusually large ionized bubble carved by exceptionally intense stellar radiation. A concentration of massive hot stars could ionize surrounding hydrogen faster than typical galaxies, creating a clear window through the cosmic fog. Perhaps the neutral hydrogen fog was patchier than models predicted, with clear channels permitting light transmission in certain directions, while other sightlines remained blocked. Perhaps the reionization process commenced earlier than standard models suggest, meaning the fog was already thinner than calculations indicated. Each explanation requires modifying aspects of established understanding about how the early universe evolved from opacity to transparency. Webb's early universe observations consistently reveal structures challenging theoretical predictions across multiple domains simultaneously. Galaxies assembled too rapidly. Black holes grew too massive. Chemical evolution progressed too quickly. The transitions from primordial to modern cosmic conditions occurred faster than models predicted. Each individual discovery forces reconsideration of assumptions that seemed secure for decades. Taken together, they suggest something fundamental about early cosmic evolution differs from theoretical expectations. The standard cosmological framework successfully explained decades of observations before Webb launched. It matched cosmic microwave background radiation patterns left over from the Big Bang with exquisite precision. It predicted galaxy distribution across observable space with statistical accuracy. It explained light element abundances forged in the first minutes of cosmic time. This framework earned scientific confidence through consistent success across multiple independent tests, spanning different cosmic epochs and physical processes. Now that framework shows stress fractures, not catastrophic failures that demand immediate abandonment, but significant discrepancies between theoretical predictions and observational reality that cannot be easily dismissed. Theorists are actively modifying models, adding new physics, adjusting parameters to accommodate what Webb reveals. Some propose that dark matter clumped more efficiently in the early universe than standard models assume, accelerating structure formation. Others suggest that primordial star formation followed different rules when the cosmos contained only hydrogen and helium without heavier elements. Still others wonder whether fundamental aspects of gravity or cosmic expansion require revision at early times. The honest assessment is that we do not yet understand what Webb's discoveries ultimately signify for cosmological theory. The telescope has operated for only a few years. Data continues streaming from its instruments with each observing cycle. New objects appear that either challenge or confirm emerging theoretical frameworks. Science requires time to test hypotheses through independent observations, discard failed explanations that do not survive scrutiny, and converge toward understanding that accommodates all available evidence. We witness the opening chapter of a revolution in cosmic knowledge, not its resolution. What remains certain is that the universe evolved differently than we believed before Webb launched. The first billion years of cosmic history were far more dynamic, far more productive, far more mysterious than any model predicted. Webb has opened a window onto this ancient epoch that no previous telescope could access due to fundamental technological limitations. Through that window, we observe a cosmos rushing toward complexity with urgency that demands explanation. The universe was not content to evolve gradually. It raced toward structure with haste that theories never anticipated. The implications extend far beyond academic cosmology into questions touching on our cosmic context. Rapid formation of massive galaxies suggests that conditions enabling planetary systems arose much earlier than previously assumed. Planets form from heavy elements created inside stars and dispersed through stellar explosions. If galaxies could construct stellar populations billions of years ahead of schedule, then rocky planets with potential for harboring life might have formed equally early. The cosmos may have been habitable for far longer than anyone imagined, potentially hosting life while Earth was still forming from primordial debris. But early universe observations also raise unsettling questions about the reliability of scientific understanding. If models failed to predict what Webb discovered, despite decades of refinement and successful predictions in other domains, what else might they have gotten wrong? The theoretical framework that successfully explained so many observations now requires significant modification to accommodate new data. Scientists must determine whether minor parameter adjustments suffice or whether more fundamental conceptual revisions become necessary. The process of scientific revision is healthy and expected, but the magnitude of required changes suggests our understanding of early cosmic evolution was more incomplete than anyone suspected. The edge of cosmic time has revealed secrets stranger than theoretical imagination anticipated. Massive galaxies exist where only primitive structures should have formed. Supermassive black holes appear where stellar mass seeds should still be growing through gradual accretion. Webb has shown that the early universe operated under conditions we are only beginning to comprehend, following rules we have not yet fully deciphered. The light from cosmic dawn carries messages across billions of years that challenge everything we thought we understood about how the universe became what it is today. And we have only begun reading those messages. Black holes represent the universe's most extreme objects. These gravitational monsters compress matter so densely that not even light can escape their pull. The boundary marking this point of no return, called the event horizon, defines a region where space-time curves so severely that all paths lead inward. Nothing that crosses this threshold ever returns to the observable universe. Black holes are cosmic one-way doors, swallowing everything that ventures too close while revealing almost nothing about conditions within their dark interiors. The concept of an object so massive that light cannot escape dates back centuries. English clergyman John Michell proposed such dark stars in 1783, reasoning that sufficiently massive objects would trap their own light through gravitational attraction. Einstein's general theory of relativity later provided the mathematical framework describing how mass warps space-time. German physicist Karl Schwarzschild calculated the first exact solution to Einstein's equations just months after their publication, describing what we now call a black hole. For decades, these objects remained theoretical curiosities that many physicists doubted could actually form in nature. Observations eventually confirmed that black holes are not merely mathematical abstractions, but genuine cosmic objects. X-ray telescopes detected radiation from gas heated to extreme temperatures as it spiraled toward unseen massive companions in binary star systems. Radio telescopes mapped jets of material launched at near-light speeds from galactic centers, powered by accretion onto compact objects. Gravitational wave detectors directly sensed space-time ripples produced when black holes merged. The existence of black holes transitioned from theoretical speculation to observational certainty through accumulating evidence across multiple detection methods. Scientists understand how typical black holes form through stellar evolution. Massive stars exhaust their nuclear fuel after millions of years of fusion reactions, converting hydrogen into helium, helium into carbon, and progressively heavier elements up to iron. Each fusion stage releases energy that generates radiation pressure, pushing outward against gravitational compression, trying to collapse the star. When iron accumulates in the stellar core, fusion can no longer proceed because iron fusion consumes energy rather than releasing it. Without radiation pressure support, the core collapses catastrophically within seconds. If the original star contained sufficient mass, this collapse produces a black hole containing between 5 and 100 times our Sun's mass. The collapsing core exceeds the density limits that even nuclear forces can resist. Matter crushes inward, until nothing can halt the compression. A singularity forms where density approaches infinity, and our understanding of physics breaks down. The event horizon surrounds this singularity, marking the boundary beyond which escape becomes impossible. These stellar mass black holes populate galaxies throughout the observable universe, remnants of massive stars that lived fast and died violently in spectacular gravitational collapse. But another class of black holes exists that defies such simple explanation. Supermassive black holes containing millions to billions of solar masses inhabit the centers of most large galaxies. Our own Milky Way hosts a supermassive black hole called Sagittarius A star, containing approximately 4 million solar masses, compressed into a region smaller than Mercury's orbit around the Sun. The giant elliptical galaxy M87 harbors a monster exceeding 6 billion solar masses, with an event horizon larger than our entire solar system. These objects dwarf stellar mass black holes by factors of millions, yet their formation pathways remain deeply mysterious despite decades of theoretical investigation. No star could ever grow massive enough to collapse into a billion solar mass black hole directly. The most massive stars observed contain perhaps 200 solar masses before radiation pressure prevents further growth. Stellar evolution cannot produce seeds anywhere near supermassive scales. Some other process must create these cosmic monsters, but identifying that process has challenged astrophysicists since supermassive black holes were first discovered powering the brilliant cores of distant quasars in the 1960s. The puzzle intensifies dramatically when considering growth rates. Black holes increase their mass by consuming surrounding material that ventures within their gravitational influence. Gas, dust, and occasionally entire stars spiral inward along orbital paths that gradually decay through friction and gravitational interactions. As material approaches the event horizon, gravitational compression heats it to temperatures exceeding millions of degrees. This superheated material glows brilliantly across the electromagnetic spectrum before crossing the event horizon and adding its mass to the black hole. This accretion process converts gravitational energy into radiation with remarkable efficiency, far exceeding nuclear fusion that powers stars. The radiation streams outward, creating pressure that pushes against infalling material. Beyond a certain accretion rate, this outward radiation pressure balances gravitational attraction, trying to pull material inward. A traffic jam develops where incoming matter cannot fall faster because radiation pushes it back. This self-regulating mechanism establishes a maximum growth rate called the Eddington limit, named after English astrophysicist Arthur Eddington, who first calculated it. A black hole accreting at this theoretical ceiling doubles its mass approximately every 45 million years. The math is straightforward but produces sobering conclusions. Starting from a stellar remnant containing 100 solar masses, reaching supermassive scales of 1 million solar masses would require roughly 600 million years of continuous maximum rate accretion without interruption. Growing to 1 billion solar masses would demand nearly 1 billion years of sustained feeding at the theoretical maximum rate. These are absolute minimum timescales, assuming perfect conditions that likely never exist in actual cosmic environments. These timescales created no problems when astronomers believed supermassive black holes formed gradually over cosmic history through patient feeding. Galaxies have existed for over 13 billion years, providing ample time to nurture their central monsters. The oldest known supermassive black holes seem to exist at cosmic times when sufficient growth time had elapsed since the first stars formed. Everything appeared consistent with gradual accretion from stellar mass seeds, even if the specific mechanisms remained unclear. The timeline worked, which was enough for comfortable theoretical frameworks. Webb shattered this comfortable picture completely. The telescope detected supermassive black holes existing when the universe was merely 500 to 700 million years old. These objects contain tens of millions of solar masses, despite the cosmos being far too young to permit such growth through standard accretion physics. Simple arithmetic reveals the impossibility with stark clarity. Even starting immediately after the first stars formed around 200 million years after the Big Bang, and accreting continuously at maximum theoretical rates without any interruption, stellar mass seeds could not have grown to observed masses within available cosmic time. The timeline does not work. Something fundamental about our understanding must be wrong. The black hole powering Canucks LRDZ 8.6 exemplifies this paradox in dramatic fashion. Webb's spectroscopic observations revealed gas orbiting a central mass concentration at velocities exceeding 1,000 kilometers per second. Such rapid orbital motion requires an enormous gravitational mass to explain. Gas does not circle empty space at such tremendous speeds. Detailed dynamical modeling confirmed that this system, existing just 570 million years after the Big Bang, hosted a supermassive black hole containing tens of millions of solar masses. The black hole was actively consuming surrounding material at rates exceeding 40 times the theoretical Eddington limit. Physics, as currently understood, simply does not permit such rapid growth. Several mechanisms might explain super-Eddington accretion in the early universe under conditions differing from modern cosmic environments. Perhaps dense gas clouds fell into black holes along specific trajectories that minimized exposure to radiation pressure. If material approaches along the rotational poles rather than through the equatorial accretion disk, it might avoid the radiation-dominated regions where outward pressure is strongest. Perhaps magnetic field configurations channeled material along paths, threading through gaps in the radiation barrier. Strong magnetic fields can funnel gas along field lines that bypass the regions where radiation pressure dominates. Perhaps the geometry of early accretion disks differed fundamentally from modern configurations in ways permitting higher mass transfer rates. Early universe gas contained almost no heavy elements, which affects how efficiently radiation couples to matter. Without heavy elements absorbing radiation efficiently, the coupling between outward radiation pressure and infalling gas might weaken, allowing faster accretion than modern calculations predict. Each possibility requires physics operating differently than standard models predict, but none violates fundamental laws if early universe conditions differed sufficiently from modern assumptions. But even super Eddington accretion cannot fully resolve the formation mystery. Where did the seed black holes originate that subsequently grew so rapidly? Standard stellar evolution produces black holes containing at most 100 solar masses through core collapse of massive stars. Growing from such modest seeds to tens of millions of solar masses in merely 500 million years requires sustained super Eddington accretion rates that strain theoretical credibility, even under optimistic assumptions. The black holes would need to feed at 40 times the Eddington limit continuously for hundreds of millions of years without significant interruption. Such sustained extreme accretion seems implausible given the chaotic environments of early galaxies. The early universe seemingly contained black holes that formed already massive through mechanisms entirely separate from standard stellar collapse pathways. These seeds started heavy, requiring far less subsequent growth to reach observed supermassive scales. But how could such heavy seeds form in a universe containing only hydrogen and helium gas without any stars to collapse? Theoretical physicists have long proposed an alternative formation pathway that sidesteps stellar evolution entirely. Direct collapse black holes form not from stellar remnants, but from massive primordial gas clouds that skip the stellar phase altogether. Under specific conditions that existed only in the early universe, enormous gas concentrations could collapse directly into black holes without ever igniting nuclear fusion and becoming stars. This process requires pristine gas containing almost no heavy elements that would enable efficient cooling and fragmentation into smaller structures. In modern star-forming regions, heavy elements like carbon and oxygen radiate energy efficiently, allowing gas clouds to cool and fragment into numerous smaller clumps. Each clump forms a separate star of modest mass. But primordial gas lacking these coolants cannot fragment efficiently. Instead, the entire massive cloud collapses together, growing ever denser and hotter. If conditions prevent the cloud from fragmenting into stars, it can collapse directly into a black hole containing the entire cloud mass. The collapse must proceed rapidly enough that no intermediate stellar phase develops. If nuclear fusion ignites before the collapse completes, the object becomes an extraordinarily massive star rather than a direct collapse black hole. The distinction matters because stellar fusion generates radiation pressure that limits how massive the resulting object can become. Direct collapse avoids this limitation by never igniting fusion, allowing black hole formation from arbitrarily massive gas clouds. Direct collapse could produce black holes containing 100,000 to 1 million solar masses almost instantaneously on cosmic timescales. These heavy seeds would require far less subsequent accretion to reach supermassive scales observed in the early universe. A direct collapse. Black hole forming with 500,000 solar masses would need only modest growth by factors of 20 to 50 to achieve the tens of millions of solar masses Webb detected in early universe systems. Such growth factors are achievable within available cosmic time, even at standard Eddington limited accretion rates. In July 2025, Webb may have captured the first direct evidence for this elusive formation process. Researchers discovered an unusual object they nicknamed the Infinity Galaxy because of its distinctive figure-8 morphology, resembling the mathematical infinity symbol. This system formed when two disk galaxies collided head-on in a cosmic pileup, creating a structure featuring two compact nuclei surrounded by rings of gas and stars thrown outward by the violent interaction. The collision triggered intense gravitational interactions that redistributed matter throughout the merged system in patterns never before observed. Between the two galactic nuclei, embedded within an enormous expanse of ionized gas glowing from intense radiation, sits a supermassive black hole containing approximately 1 million solar masses. This black hole occupies an extremely unusual location that immediately attracted researcher attention. Supermassive black holes normally reside at galactic centers, where they either formed originally or migrated over cosmic time through gravitational interactions. Finding one between galactic centers, surrounded by gas but lacking any significant stellar population, defied conventional expectations for where such objects should exist. The configuration strongly suggests the black hole formed in place rather than migrating from either galactic nucleus after forming through conventional means. The collision between galaxies apparently created conditions favorable for direct collapse that normally cannot occur in isolated systems. A massive gas cloud caught between the merging systems, compressed by converging gravitational forces from both directions, may have skipped stellar evolution entirely. The cloud collapsed directly into a black hole seed that subsequently grew to its current million solar mass scale through accretion from surrounding gas made plentiful by the galactic collision. Multiple independent observations from different telescopes and wavelength ranges support this extraordinary interpretation. NASA's Chandra X-ray Observatory detected high-energy emission consistent with active accretion onto a massive compact object. X-rays are produced when gas heats to millions of degrees while spiraling toward a black hole, providing diagnostic signatures that distinguish accreting black holes from other cosmic sources. Radio telescopes identified emission patterns matching theoretical predictions for gas falling into a supermassive black hole, including jets of material launched perpendicular to the accretion disk. The mass estimate derived from gas dynamics places this object firmly in supermassive territory despite its unusual location between galactic centers rather than at either center. If confirmed through additional observations and analysis, the Infinity Galaxy discovery represents the first direct evidence for a formation mechanism theorists proposed decades ago, but could never previously test observationally. Direct collapse black holes could explain how supermassive objects appeared so early in cosmic history when insufficient time existed for conventional growth pathways. Instead of requiring billions of years of gradual growth from stellar mass seeds that seemed inadequate to explain observations, these monsters could form already massive through catastrophic gas cloud collapse under conditions unique to the early universe. The early universe may have been filled with direct collapse events that planted heavy black hole seeds, subsequently growing into the supermassive black holes inhabiting modern galactic centers. Each massive galaxy we observe today might trace its central black hole back to a direct collapse event occurring within the first billion years of cosmic history. The black holes we previously thought developed slowly over cosmic time may instead be ancient relics from the cosmic dawn, formed through processes that no longer operate in the modern universe. But Webb's black hole discoveries extend well beyond formation and growth mysteries into even stranger territory. In December 2025, the telescope confirmed the first directly observed runaway supermassive black hole. This extraordinary object had been violently ejected from its host galaxy and now travels through intergalactic space at tremendous velocity, like a cosmic bullet fired from a galactic gun. The discovery came from observations of a system designated the Cosmic Owl, located approximately 8.8 billion light-years from Earth in the direction of the constellation Virgo. The Cosmic Owl consists of two ring galaxies undergoing gravitational merger. Ring galaxies form when smaller galaxies punch through the centers of larger disk galaxies, creating expanding density waves that pile up stars and gas into ring structures. Finding two such objects interacting provided a rare opportunity to study extreme gravitational dynamics. Webb's spectroscopic observations of this system revealed signatures consistent with something entirely unexpected: a supermassive black hole traveling supersonically through ambient gas between the merging galaxies. The telescope detected both a trailing wake behind the black hole where gas has been disturbed by its passage, and a bow shock in front, where the object plows through surrounding material faster than sound waves can propagate. These features create distinctive spectral signatures, as gas is compressed, heated, and ionized by the passing gravitational monster. The observations match theoretical predictions for ejected black holes that astrophysicists had calculated decades ago but never observed directly until Webb captured the cosmic owl system. Ejecting a supermassive black hole from a galaxy requires extraordinary circumstances that strain imagination. These objects typically anchor themselves at galactic centers through overwhelming gravitational dominance over everything else in their host systems. A black hole containing millions of solar masses gravitationally binds stars orbiting within thousands of light years. Dislodging something this gravitationally dominant demands energy inputs that only the most violent cosmic events can provide. The black hole must be accelerated to velocities exceeding the escape speed of its host galaxy, which for massive galaxies reaches thousands of kilometers per second. Two mechanisms can generate sufficient ejection velocities under specific circumstances. During galaxy mergers, multiple supermassive black holes sometimes end up interacting gravitationally within the same merged system. Each merging galaxy contributes its own central black hole, and if a third galaxy joins the merger, three massive black holes can orbit each other in complex gravitational dances. If two black holes merge while a third orbits nearby, the gravitational slingshot effect can accelerate the remaining single black hole to velocities exceeding galactic escape speed. The merged pair recoils in one direction from gravitational wave emission, while the third black hole flies off in another direction, potentially achieving velocities of several thousand kilometers per second. Alternatively, when two black holes merge into a single larger black hole, they emit gravitational waves carrying away energy and momentum. If this gravitational wave emission occurs asymmetrically, due to differences in the merging black hole's masses or spins, the merged remnant receives a recoil kick in the direction opposite to the stronger gravitational wave emission. Theoretical calculations show that specific merger configurations involving rapidly spinning black holes with particular orientations can produce recoil velocities exceeding 4,000 kilometers per second. This exceeds the escape velocity from even the most massive galaxies, launching the merged black hole into intergalactic space permanently. The cosmic owl observation provides direct evidence that these theoretical ejection mechanisms actually occur in nature, transforming mathematical predictions into confirmed astrophysical reality. The runaway black hole continues traveling through intergalactic space at velocities that will carry it millions of light years from its origin. It interacts with gas clouds along its path, generating observable signatures that Webb can detect across billions of light years of cosmic distance. Future observations may reveal additional runaway black holes traveling through the cosmic void, enabling statistical studies of how frequently ejection events occur and what specific conditions trigger these violent expulsions. Perhaps the most profound black hole mystery Webb has illuminated involves not the black holes themselves, but their potential progenitors. Objects so massive they challenge conventional stellar physics. In December 2025, an international research team announced discovery of chemical evidence for monster stars that existed in the early universe. These hypothetical supermassive primordial stars weighed between 1,000 and 10,000 times our Sun's mass, far exceeding any star that could form under modern cosmic conditions. They may explain both unusual chemical abundances observed in early galaxies and the origins of the first supermassive black holes through a single unified mechanism. The discovery emerged from painstaking analysis of the spectrum of galaxy GS 3073, an ancient system whose light reveals conditions existing billions of years ago. Researchers found an extreme imbalance between nitrogen and oxygen abundances that no known stellar population could produce through any combination of masses, ages, or chemical compositions. Normal stars generate specific elemental ratios through nuclear fusion processes that convert lighter elements into heavier ones. The nitrogen-to-oxygen ratio observed in GS 3073 exceeded any ratio producible by ordinary stellar populations, regardless of what assumptions researchers made about the stellar population properties. The spectrum demanded an explanation beyond conventional stellar physics. Some exotic process must have operated in this galaxy that cannot occur in modern star-forming environments. After exhaustive comparison with theoretical models, researchers identified supermassive primordial stars as the only viable explanation for the observed chemical anomaly. Theoretical models had predicted that supermassive stars could form in the early universe under conditions that no longer exist anywhere in the modern cosmos. Primordial gas consisted almost entirely of hydrogen and helium, without the heavier elements that help gas clouds cool efficiently and fragment into smaller structures. In modern star-forming regions, heavy elements like carbon, oxygen, and iron radiate energy that allows gas to cool rapidly. Cool gas fragments into numerous smaller clumps, with each clump forming a separate star of modest mass, typically ranging from 1/10 to 100 solar masses. Without heavy element coolants, primordial gas clouds behaved completely differently. Instead of breaking into many small stars, the entire massive cloud collapsed together as a single unit. The resulting object achieved masses impossible under modern conditions, potentially reaching 10,000 solar masses or more before nuclear fusion ignited in its core. These supermassive primordial stars would have been cosmic monsters without parallel in the subsequent universe. Such extreme stellar objects would have burned through their nuclear fuel in just a few million years, brief lifetimes, even by stellar standards. Their enormous masses drove fusion reactions at rates vastly exceeding those in ordinary stars, consuming available fuel rapidly despite the larger fuel supply. When they exhausted their hydrogen cores, these monsters faced catastrophic fates. Stars exceeding certain mass thresholds collapsed directly into black holes without passing through explosive supernova phases that disperse most stellar mass into surrounding space. A 10,000 solar mass primordial star could collapse into a black hole retaining most of its original mass, providing exactly the heavy seeds needed to explain early supermassive black hole populations. The research team, analyzing GS 3073, found that the required nitrogen enrichment signatures only appear within specific stellar mass ranges that match theoretical predictions precisely. Stars smaller than 1,000 solar masses fail to produce sufficient nitrogen relative to oxygen, regardless of other assumptions. Stars larger than 10,000 solar masses produce different chemical signatures that do not match observations. Only stars within the 1,000 to 10,000 solar mass range generate the observed nitrogen-to-oxygen ratio. This mass window matches theoretical predictions for supermassive primordial stars, providing independent confirmation that these objects actually existed. Intriguingly, Galaxy GS 3073 contains an actively feeding black hole at its center, whose properties are consistent with being a direct remnant of supermassive primordial stellar evolution. This black hole might represent the collapsed corpse of one of the monster stars that enriched the galaxy with nitrogen through nuclear burning before meeting its gravitational doom. If this interpretation is confirmed through additional observations, a single discovery would solve two major mysteries simultaneously. The extreme nitrogen abundance results from nuclear burning in monster stars. The central black hole represents the gravitational remnant of such a star after core collapse. One observation explains both early chemical enrichment and early black hole formation through a unified physical mechanism. The implications of supermassive primordial stars cascade throughout early cosmic history, affecting multiple aspects of how the universe evolved from primordial simplicity to modern complexity. Monster stars burning intensely for brief lifetimes would have produced enormous quantities of ultraviolet radiation. This radiation would have ionized surrounding hydrogen gas, contributing significantly to cosmic reionization that transformed the universe from opaque neutral fog to transparent ionized plasma. The transition to transparency that allowed light to travel freely across cosmic distances may have been driven substantially by supermassive primordial stars rather than ordinary stellar populations. When these monster stars died, their supernova explosions or direct collapses would have seeded surrounding space with heavy elements forged through nuclear fusion. These elements enabled subsequent stellar generations to form with different properties than primordial populations. Planets require heavy elements like silicon, iron, and oxygen to form rocky surfaces. Life as we know it requires carbon, nitrogen, and other elements heavier than hydrogen and helium. The heavy elements that made planetary systems and biological evolution possible may trace back to nuclear burning in supermassive primordial stars that lived and died within the first few 100 million years of cosmic history. The black hole remnants these monster stars left behind would have provided exactly the heavy seeds needed for supermassive black hole growth. Instead of starting from modest stellar mass black holes and requiring implausible sustained super-Eddington accretion, early black hole growth could have started from seeds already containing thousands to tens of thousands of solar masses. Such seeds require far less subsequent growth to reach the millions of solar masses Webb has detected in early universe systems. Supermassive primordial stars may represent the missing link connecting the primordial universe of hydrogen and helium to the black hole-dominated galactic centers we observe today. Webb has opened observational windows onto black hole phenomena that remained purely theoretical before the telescope launched. Direct collapse black holes forming from primordial gas clouds without passing through stellar phases. Runaway supermassive black holes violently ejected from merging galaxy systems and traveling through intergalactic void. Monster stars that seeded early black hole formation through catastrophic gravitational collapse after brief but brilliant lifetimes. Super-Eddington accretion, permitting rapid mass growth beyond limits calculated from modern physics. Each phenomenon had been predicted mathematically by theorists, but lacked observational confirmation until Webb provided evidence that these exotic processes actually occurred in the early universe. The black holes populating the early universe broke rules governing black hole physics in the modern cosmos. They formed through pathways that no longer operate under current cosmic conditions. They grew at rates exceeding theoretical limits, derived from observations of modern accreting systems. They achieved masses that would require billions of years of evolution through conventional processes in cosmic timespans measured in mere hundreds of millions of years. Understanding how this happened requires fundamentally rethinking aspects of black hole physics and cosmic evolution that seemed settled before Webb revealed how strange the early universe truly was. Some researchers suggest the early universe simply operated under physical conditions so different from today that our modern intuitions fail completely. Primordial gas had different composition without heavy elements, different temperature distributions without stellar heating, and different dynamical properties without established galactic structures. These differences enabled formation and growth mechanisms impossible in the chemically enriched, dust-filled, galaxy-dominated environments characterizing contemporary cosmic conditions. The black holes Webb detected are not violations of physics, but products of conditions that no longer exist anywhere in the modern universe. Others propose that our understanding of black hole physics itself requires revision, even for modern conditions. Perhaps the Eddington limit is less strict than idealized spherical calculations suggest when realistic accretion geometries are considered. Perhaps accretion disk configurations permit higher mass transfer rates than theoretical models based on limited observational constraints predict. Perhaps magnetic fields, relativistic effects, or other factors modify the relationship between radiation, pressure, and gravitational infall in ways that increase maximum accretion rates. Webb's observations of early universe black holes may reveal gaps in understanding that extend beyond early cosmic conditions to fundamental accretion physics applicable everywhere. Whatever explanations ultimately prove correct after years of additional observation and theoretical development, Webb has already demonstrated conclusively that supermassive black holes are not merely the mature products of billions of years of gradual patient evolution. They are ancient features of the cosmic landscape, present in their essential form, almost from the beginning of cosmic structure formation. The universe did not slowly develop supermassive black holes over leisurely timescales. as galaxies gradually fed their central appetites. It created them rapidly, violently, through mechanisms we are only beginning to comprehend after decades of theoretical speculation, finally meeting observational reality. The monsters lurking at the centers of galaxies throughout the cosmos formed during the cosmic dawn when the universe was young, and Webb has finally revealed just how strange and rapid their origins truly were. Humanity has wondered for millennia whether other worlds exist beyond Earth. Ancient philosophers debated the possibility of cosmic plurality, imagining countless worlds scattered throughout the heavens. Democritus proposed infinite universes containing infinite Earths. Epicurus argued that the vastness of space demanded other worlds where life might flourish. Giordano Bruno was burned at the stake, partly for insisting that stars were distant suns orbited by their own planets. The question of whether we are alone has driven scientific inquiry and philosophical speculation across countless generations, touching the deepest questions about human significance in the cosmos. For most of history, this question remained purely philosophical because technology could not address it observationally. Stars appeared as dimensionless points of light, even through the most powerful telescopes. Any planets orbiting those distant suns would be lost in overwhelming stellar glare, invisible to instruments designed to collect and focus light. Detecting a planet next to its host star resembles spotting a firefly hovering beside a searchlight from thousands of miles away. The brightness ratio between stars and their planets ranges from millions to billions, creating observational challenges that seemed insurmountable for centuries. The first confirmed exoplanet orbiting a Sun-like star was discovered in 1995 by Swiss astronomers Michel Mayor and Didier Queloz. They detected a massive planet orbiting the star 51 Pegasi by measuring tiny wobbles in the star's motion caused by gravitational tugging from an unseen companion. This radial velocity technique revealed a planet roughly half Jupiter's mass, orbiting closer to its star than Mercury orbits our Sun, completing full orbits in just 4 days. The discovery of this hot Jupiter shattered assumptions about planetary system architecture and launched a new era of exoplanet science. Since then, astronomers have detected thousands of worlds orbiting distant stars using increasingly sophisticated techniques. Transit photometry measures the slight dimming when planets pass in front of their host stars, blocking a tiny fraction of stellar light. NASA's Kepler Space Telescope revolutionized this approach by staring at over 150,000 stars simultaneously for years, catching thousands of planetary transits. Radial velocity spectroscopy continues detecting gravitational wobbles with ever-increasing precision. Direct imaging captures photons reflected or emitted by planets themselves, though this technique remains limited to young, massive planets orbiting far from their host stars. Each method reveals different planetary properties, and combining multiple techniques provides comprehensive characterization of distant worlds. But detection and understanding are fundamentally different achievements in planetary science. Knowing a planet exists reveals almost nothing about its true nature, beyond basic orbital and physical parameters. Is the world rocky like Earth or gaseous like Jupiter? Does it possess an atmosphere capable of supporting liquid water on its surface? What chemical compounds dominate its atmospheric composition? Could conditions on its surface or within its atmospheric layers permit biological activity of any kind? These profound questions remained largely unanswerable for most known exoplanets, until Webb brought unprecedented spectroscopic capabilities to bear on alien world characterization. Webb analyzes starlight that has passed through planetary atmospheres during transit events with sensitivity no previous instrument could achieve. As planets cross in front of their host stars from our viewing perspective, a tiny fraction of stellar light filters through the thin atmospheric shell surrounding the planetary disk, before continuing toward Earth. Different atmospheric gases absorb specific wavelengths of light according to their molecular structures, creating spectral fingerprints that reveal chemical composition to instruments sensitive enough to detect them. Webb's infrared sensitivity enables detection of molecules invisible to optical telescopes, including water vapor, carbon dioxide, methane, and other compounds critical for understanding planetary environments and potential habitability. The technique requires extraordinary precision. Planetary atmospheres block perhaps 1 part in 10,000 of their host star's light during transit. Detecting which specific wavelengths are absorbed at slightly higher rates than others demands stable instruments, long observation times, and careful analysis that accounts for instrumental artifacts and stellar variability. Webb's position beyond Earth's atmosphere eliminates absorption by our own planet's air, while its large mirror collects enough photons to achieve the signal-to-noise ratios necessary for reliable molecular detection in distant planetary atmospheres. In December 2025, Webb delivered what researchers described as the strongest evidence yet for an atmosphere surrounding a rocky planet outside our solar system. The target was TOI 561b, an ultra-short-period super-Earth discovered by NASA's Transiting Exoplanet Survey satellite. This world completes full orbits around its host star in less than 11 hours, racing around at speeds exceeding 140 kilometers per second. Such extreme proximity subjects the planet to intense stellar radiation that heats the day-side surface to temperatures exceeding 2200 degrees Fahrenheit, well above the melting points of most common rock-forming minerals. Scientists expected this broiling world to be stripped bare of any atmospheric envelope. Intense stellar radiation should drive atmospheric escape through multiple mechanisms. High-energy photons heat upper atmospheric layers until gas molecules achieve velocities exceeding escape speed. Stellar wind particles impact the atmosphere, transferring momentum that pushes gas into space. Close-in planets also experience tidal forces that can enhance atmospheric loss. Every theoretical consideration suggested that TOI 561b should be airless rock baking under relentless stellar bombardment, its primordial atmosphere long since blasted away. Webb observed TOI 561b continuously for more than 37 hours, capturing 4 complete orbital cycles as the planet swung around its star. The telescope measured thermal emission from the planet at different orbital phases, tracking how temperature varied between the perpetually illuminated dayside and the dark nightside hemisphere. This phase curve technique reveals how efficiently heat redistributes across planetary surfaces. Bare rock worlds show extreme temperature contrasts because rock conducts heat poorly, leaving the night side frigid while the day side broils. Atmospheres redistribute thermal energy through wind circulation, carrying heat from illuminated regions to dark regions and reducing the temperature difference between hemispheres. TOI 561b displayed heat redistribution patterns consistent with a substantial atmospheric envelope rather than bare rock. The night side was significantly warmer than any airless rock model could predict, indicating that atmospheric circulation was actively transporting energy from the superheated day side around to the dark hemisphere. The planet apparently maintains a thick atmosphere, despite surface conditions that should vaporize stone and drive rapid atmospheric escape. The day side likely consists of a global magma ocean, continuously outgassing volatile materials, including silicate vapors, sodium, and other rocky constituents that replenish atmospheric losses from ongoing stellar stripping. This discovery fundamentally challenges prevailing assumptions about atmospheric retention on close-in rocky planets that informed habitability assessments across the exoplanet catalogue. Conventional wisdom held that intense stellar radiation would inevitably strip atmospheres from worlds orbiting within extreme proximity to their host stars within geologically short timescales. TOI 561b demonstrates that at least some rocky planets can maintain substantial atmospheric envelopes under conditions previously thought absolutely prohibitive for atmospheric retention. The outgassing mechanism may sustain atmospheres indefinitely, as long as sufficient volatile material remains in planetary mantles to replenish ongoing losses. The implications for planetary habitability extend far beyond this single scorched world. If rocky planets can retain atmospheres, even under hostile stellar bombardment through continuous outgassing and other mechanisms, then far more planets throughout the galaxy may possess the atmospheric pressure necessary for liquid surface water than pessimistic models suggested. Atmospheric retention appears less fragile than theoretical calculations indicated, potentially expanding the range of environments where surface conditions might support biological activity. But Webb's most tantalizing exoplanet discovery may orbit a star visible to the naked eye on any clear night from either hemisphere. In August 2025, astronomers announced strong evidence for a giant planet orbiting Alpha Centauri A, one of the three stars comprising the nearest stellar system to our Sun. At just over 4 light-years distance, this potential world would be the nearest exoplanet orbiting in the habitable zone of a Sun-like star ever detected. Confirmation would fundamentally transform our understanding of the immediate cosmic neighborhood and provide an unprecedented target for future characterization efforts. Alpha Centauri is actually a triple star system. Alpha Centauri A and B form a close binary pair, orbiting each other every 80 years at distances ranging from 11 to 36 times the Earth-Sun separation. The third component, Proxima Centauri, is a small red dwarf orbiting the central pair at enormous distance, taking hundreds of thousands of years to complete each orbit. Proxima already hosts at least 2 confirmed planets, including Proxima b orbiting in the habitable zone. But Proxima is a red dwarf prone to violent flares that may render its planets uninhabitable. Alpha Centauri A is a Sun-like star, offering potentially more clement conditions for any orbiting worlds. The detection pushed Webb's capabilities to absolute limits never anticipated during mission design. Alpha Centauri A is extraordinarily bright compared to typical exoplanet host stars, roughly 10 million times brighter than the faint distant sources Webb was optimized to study. Its companion Alpha Centauri B adds additional complicating light to the observational field. The telescope's instruments were optimized for detecting faint sources at cosmic distances, not blocking overwhelming glare from stellar neighbors so close they exhibit measurable proper motion across the sky. Mission operators developed custom observing sequences specifically for this challenging target that required months of planning and testing. Webb's mid-infrared instrument employed a coronagraphic mask to block the overwhelming stellar light, creating an artificial eclipse that revealed fainter sources in the surrounding region. Even with this mask, residual stellar light scattered through the optical system created artifacts that could mimic planetary signals. Detecting a genuine planetary companion required pushing instrumental sensitivity to extreme limits, while carefully modeling and subtracting residual stellar contamination through sophisticated data processing. In August 2024, Webb detected a faint infrared source, approximately 10,000 times dimmer than Alpha Centauri A itself. The source appeared at a projected separation of approximately 1.1 arcseconds, corresponding to an orbital distance roughly twice the Earth-Sun separation at Alpha Centauri's distance. If this source represents a genuine planetary companion, rather than a background object or instrumental artifact, it would orbit within the star's habitable zone, where liquid water could theoretically exist on planetary surfaces or on moons orbiting the planet. Subsequent observations created a deeply puzzling mystery that researchers are still working to resolve. When Webb observed the Alpha Centauri system again in February and April 2025, the detected source had completely vanished. No trace remained at the location where the bright infrared source had appeared months earlier. The research team faced what they termed a disappearing planet problem that demanded explanation. Had the original detection been spurious noise amplified by statistical fluctuation? Had a distant background galaxy briefly aligned with Alpha Centauri before drifting away? Had instrumental artifacts created a false positive that subsequent observations failed to reproduce? Or had a genuine planet simply moved along its orbit to a location where Webb could no longer distinguish it from stellar glare? Computer simulations explored millions of possible orbital configurations that could potentially explain both the initial detection and subsequent non-detections without invoking spurious signals. The modeling revealed that planets on elliptical orbits could easily produce exactly this observational pattern through normal orbital motion. If the planet's orbit carries it close to the star during certain orbital phases, it would be completely lost in stellar glare, even with coronagraphic masking that works well at larger separations. The simulations determined that approximately 52% of gravitationally stable orbits around Alpha Centauri A would generate the observed detection then disappearance signature purely through orbital geometry. The proposed planet would contain roughly the mass of Saturn based on its infrared brightness and assumed temperature. As a gas giant, it could not support life as we understand it on its surface, which consists of gradually thickening atmosphere rather than solid ground. However, gas giants commonly host substantial moon systems that might offer more favorable conditions. Jupiter possesses 4 large Galilean moons plus dozens of smaller satellites, including Europa with its subsurface liquid water ocean. Saturn hosts Titan, a moon larger than the planet Mercury possessing a dense nitrogen atmosphere and surface lakes of liquid hydrocarbons. A Saturn-mass planet in Alpha Centauri A's habitable zone might host moons with conditions far more favorable for habitability than the gas giant itself. Confirmation requires additional observations, catching the planet at orbital positions where it remains visible against stellar glare. The research team continues monitoring the Alpha Centauri system through ongoing Webb programs, hoping to redetect the source when orbital geometry becomes favorable. The Nancy Grace Roman Space Telescope, scheduled for launch in 2027, carries coronagraphic instruments specifically designed for imaging exoplanets around nearby stars at smaller angular separations than Webb can achieve. If a planet truly orbits Alpha Centauri A, Roman should be capable of definitive confirmation and detailed atmospheric characterization that would reveal its true nature. Webb has also revealed extraordinary atmospheric phenomena on previously known exoplanets that challenge theoretical understanding and expand the catalogue of planetary behaviors. WASP 107b is classified as a superpuff planet, meaning it has remarkably low density for its measured mass that places it among the least dense planets known. This world contains approximately Neptune's mass but inflated to Jupiter's radius, making its average density similar to cotton candy. Its puffy atmosphere extends far beyond what gravitational binding should permit, suggesting active processes driving atmospheric expansion and escape into surrounding space. In December 2025, Webb captured dramatic evidence of this ongoing atmospheric loss that exceeded all expectations for atmospheric escape rates. The telescope detected broad streams of helium gas pouring off the planet in vast quantities, creating an extended envelope around the world far exceeding its nominal atmospheric boundary. The escaping helium formed both leading and trailing structures as the planet orbited its star, tracing asymmetric tail-like features that recorded the planet's motion through surrounding circumstellar space like a cosmic comet. Webb's observations represented the first comprehensive study tracking atmospheric escape from an exoplanet continuously across a complete orbital cycle. The helium outflow proved continuous rather than episodic, indicating sustained mass loss driven by intense stellar irradiation rather than intermittent events. Extreme ultraviolet radiation from the host star heats the planet's upper atmosphere until helium atoms achieve velocities exceeding escape speed, streaming off into space in a continuous wind. The escaping gas extends enormous distances from the planet, filling substantial volumes of circumstellar space with material stripped from the planetary atmosphere. Alongside escaping helium, Webb detected water vapor and various chemical compounds in WASP 107b's deeper atmospheric layers that remained gravitationally bound. The telescope identified signatures of sulfur dioxide produced through photochemical reactions in the upper atmosphere. Curiously absent from the spectrum was methane, which theoretical equilibrium chemistry models strongly predicted should form abundantly under the planet's temperature and pressure conditions. Carbon and hydrogen are both present, and thermodynamic calculations indicated they should combine predominantly into methane at WASP 107b's temperatures. The methane deficit suggests complex atmospheric chemistry operating through pathways not captured by standard equilibrium models. Atmospheric mixing may transport gas from deep hot layers where methane is destroyed to observable altitudes faster than methane can reform. Photochemical reactions driven by stellar radiation may convert methane into other compounds. Understanding why methane fails to form despite conditions seemingly favorable for its production may reveal new aspects of exoplanet atmospheric physics applicable across the diverse catalogue of known worlds. The comprehensive observations revealed a world undergoing active transformation on timescales shorter than its host star's lifetime. WASP 107b, likely formed in the cold outer regions of its planetary system, where low temperatures and abundant ice allowed the accretion of extensive gaseous envelopes producing puffy, low-density structures. Subsequent orbital migration through gravitational interactions with other planets or the protoplanetary disk carried it inward to its current close orbit, where intense stellar radiation now strips its atmosphere into space at measurable rates. Over cosmic timescales much shorter than the system's age, WASP 107b may lose much of its gaseous envelope, potentially transforming from a puffy Neptune-like world into a denser core resembling a super-Earth. Even stranger was Webb's discovery of a hot Jupiter exhibiting twin gas tails that defy straightforward explanation using existing atmospheric models. WASP 121b orbits so close to its host star that it completes full orbits in just 30 hours, perpetually showing one face toward its star while the opposite hemisphere remains in eternal darkness. Dayside surface temperatures exceed 4,200 degrees Fahrenheit, hot enough to vaporize iron and other metals that form clouds in the planet's extreme atmosphere. The intense stellar radiation was expected to drive substantial atmospheric escape similar to WASP 107b, but Webb revealed an unexpected and unexplained configuration. The planet streams helium in two distinct tails extending in opposite directions from the planetary body. Standard atmospheric escape models predict gas flowing away from the illuminating star in a single tail structure, like cometary material streaming behind as comets approach the sun and their ices sublimate under solar heating. WASP 121b instead displays twin tails extending both toward and away from the star that current theoretical frameworks struggle to explain through conventional atmospheric physics. The symmetric structure suggests processes operating that models have not yet incorporated. Researchers are investigating several possible explanations for this bizarre geometry. Unusual magnetic field configurations might channel escaping gas along field lines that direct flow in multiple directions. Complex three-dimensional wind patterns in the planet's extreme atmosphere might produce outflows at various latitudes that project into the observed twin-tail structure. Interactions between the escaping atmosphere and the stellar wind might shape the outflow geometry in unexpected ways. The observation demonstrates conclusively that exoplanet atmospheres can behave in ways existing models completely fail to predict, highlighting how much remains unknown about atmospheric physics under conditions far different from any solar system world. Webb devoted substantial observing time to one of the most promising planetary systems for habitability research. TRAPPIST-1 contains 7 Earth-sized rocky planets orbiting a small red dwarf star just 39 light-years from Earth. The system's remarkable architecture places all 7 planets closer to their star than Mercury orbits our Sun, yet 3 of these worlds orbit within the star's habitable zone, where stellar heating could potentially maintain liquid surface water. The system has generated enormous scientific and public interest since its discovery, as perhaps the best nearby laboratory for studying potentially habitable Earth-sized worlds. Results from extensive Webb observations have dampened some of that initial enthusiasm about TRAPPIST-1's habitability prospects. The 2 innermost planets, TRAPPIST-1b and TRAPPIST-1c, show no evidence for substantial atmospheres in repeated spectroscopic observations. These worlds appear to be bare rock, their primordial atmospheric envelopes long since stripped away by radiation from their host star. Red dwarf stars like TRAPPIST-1 produce intense ultraviolet and X-ray radiation, especially during their active youth, driving atmospheric escape from close-in planets that may render them permanently uninhabitable. The third planet, TRAPPIST-1d, similarly lacks detectable Earth-like atmospheric signatures, despite orbiting in a region where liquid water could theoretically exist if atmospheric pressure were sufficient. Webb searched for carbon dioxide, water vapor, and other molecules expected in terrestrial atmospheres but found no convincing detections. Either this world also lacks substantial atmosphere, or its atmospheric composition differs dramatically from Earth's in ways that make detection more challenging. The outer planets in the TRAPPIST-1 system remain under active investigation, with results that are intriguing but highly uncertain. TRAPPIST-1e has generated the most interesting but ambiguous signals among the potentially habitable worlds. Some Webb observations hint at possible methane absorption in the planet's spectrum, which could indicate biological activity producing this gas, as on Earth, or geological processes like volcanism releasing methane from the planetary interior. Either source would suggest an active world with ongoing chemistry rather than a dead, airless rock. However, significant complications, the cloud interpretation of the TRAPPIST-1e data that prevent definitive conclusions. Red dwarf stars like TRAPPIST-1 display complex atmospheric behavior, including star spots, faculae, and atmospheric variability that can contaminate spectroscopic observations of transiting planets. When a planet crosses a spotted region of its star, the spectrum changes in ways that can mimic or mask planetary atmospheric signatures. The potential methane signature detected in some TRAPPIST-1e observations might originate from the star itself or from instrumental systematic effects rather than from any genuine planetary atmosphere. Scientists urge appropriate caution in interpreting the TRAPPIST-1e data until additional observations can resolve the ambiguity. Distinguishing genuine planetary atmospheric signatures from stellar contamination and instrumental artifacts requires multiple independent observations using different instrumental configurations across various epochs. Activity level varies. Future Webb programs will continue monitoring TRAPPIST-1e through additional transits to determine whether the methane hints represent real planetary chemistry, pointing toward habitability, or merely confounding signals from the star and instruments. Webb achieved a historic milestone by directly imaging an exoplanet for the first time, using its own instruments without relying on previous discoveries made by other telescopes. All previous Webb exoplanet characterization relied on indirect detection methods developed over preceding decades. Radial velocity spectroscopy detects gravitational wobbles induced in stellar motion. Atmospheric spectroscopy analyzes starlight filtered through planetary atmospheres during transit. Each method infers planetary presence and properties without directly capturing photons from the planets themselves. Direct imaging represents fundamentally different observational approach that captures actual photons originating from planets themselves, seeing them as distinct points of light spatially separated from their host stars. This technique enables observations impossible through indirect methods, including characterization of non-transiting planets and detailed study of planetary emission spectra uncontaminated by starlight. However, direct imaging faces extraordinary technical challenges from the overwhelming brightness contrast between stars and planets that makes the planets essentially invisible next to their hosts. Coronographic techniques that block starlight help by creating artificial eclipses that suppress the stellar glare, but cannot completely eliminate scattered light that contaminates the regions where planets might be found. Only planets orbiting at substantial angular separations from relatively faint host stars currently fall within reach of direct imaging capabilities. Young planets remain warm from their formation and thus brighter in infrared wavelengths than older cooled planets, making young planetary systems preferred targets. Webb's first directly imaged exoplanet orbits TWA-7, a young star located approximately 111 light-years from Earth in the TW Hydrae stellar association. At just 6.4 million years old, this stellar system retains a substantial debris disk, containing 3 distinct rings of material left over from the planetary formation epoch. Debris disks are signposts indicating dynamical activity, often shaped by gravitational influences from planets orbiting within the disk. Webb detected a faint infrared source located in the gap between the innermost and middle debris rings, precisely where a planet's gravitational influence would clear debris from the disk through orbital resonances. The detected object has infrared brightness, consistent with a planet containing roughly 1/3 of Jupiter's mass, radiating residual heat from its recent formation. Its position within the debris disk gap matches theoretical predictions for how planets sculpt surrounding material through gravitational interactions over millions of years. Detailed statistical analysis indicates that the probability of this source being a background galaxy, distant star, or other unrelated object is less than 1%. If confirmed through follow-up observations showing common proper motion with the host star, this detection demonstrates Webb's capability to directly image planets around other stars, opening entirely new pathways for exoplanet discovery and characterization beyond transit and radial velocity methods. Webb also investigated what may be the first exoplanet moon-forming disk ever directly measured and characterized, capturing a planetary system in an evolutionary stage never before observed. CT-Char b is a young giant planet orbiting its host star at orbital distances comparable to Pluto's orbit around our Sun, placing it in the cold outer reaches of its planetary system. Previous observations using ground-based telescopes had detected excess infrared emission beyond what the planet alone should produce, suggesting circumplanetary material surrounding the young giant. But characterizing this material in detail required Webb's infrared sensitivity and angular resolution capabilities. Webb's observations confirmed a disk of gas and dust orbiting the planet itself, rather than the star, similar in structure to the protoplanetary disks from which planets form around young stars. This circumplanetary disk contains raw material from which moons will eventually coalesce through the same accretion processes that built planets from the protoplanetary disk surrounding the young Sun. Jupiter's 4 large Galilean moons almost certainly formed from a similar circumplanetary disk orbiting the young giant planet roughly 4.5 billion years ago. Saturn's extensive moon system likely shares similar origins. Webb has captured a moon-forming system in action, revealing directly how satellite systems develop around giant planets during the final stages of planetary system assembly. Each exoplanet observation, Webb conducts advances understanding of how planetary systems form, evolve, and potentially support life in ways that connect individual discoveries to broader questions about cosmic habitability. Atmospheres retained under hostile conditions far more extreme than any solar system world. Experiences expand the theoretical range of potentially habitable environments throughout the galaxy. Giant planets orbiting in habitable zones around nearby sun-like stars raise tantalizing possibilities for habitable moons that might host surface conditions far more clement than their parent worlds. Bizarre atmospheric dynamics that no theoretical model predicted challenge scientists to develop more comprehensive frameworks for understanding planetary atmospheres under diverse conditions. Missing molecules where equilibrium chemistry demands their presence reveal disequilibrium processes that models must incorporate. Twin tails flowing in impossible directions highlight gaps in understanding that direct future theoretical development. The diversity of worlds populating our galaxy exceeds anything imagined when exoplanet science began just 3 decades ago. Webb is systematically characterizing alien worlds in ways that transform ancient philosophical speculation about cosmic plurality into rigorous observational science, subject to empirical test. Each observation constrains possibilities while opening new questions. The ultimate question of whether life exists beyond Earth remains unanswered, but the search has never been more sophisticated, more sensitive, or more informed by detailed understanding of planetary environments throughout the nearby galaxy. Webb has shown that planets are everywhere, that their diversity exceeds imagination, and that characterizing their atmospheres reveals chemical complexity that may someday include biosignatures pointing toward life beyond our world. The cosmos beyond our solar system commands attention with its exotic mysteries and mind-bending scales. Galaxies forming at cosmic dawn when the universe was barely old enough to host stars. Black holes defying theoretical limits by growing too massive too quickly. Alien worlds with atmospheres exhibiting chemistry unlike anything in human experience. These distant phenomena capture imagination and dominate scientific headlines with discoveries that challenge fundamental understanding. Yet some of Webb's most consequential and personally relevant discoveries have come not from the depths of extragalactic space, but from our immediate planetary neighborhood. The worlds orbiting our sun harbor secrets that Webb's infrared vision has begun revealing in unprecedented detail, transforming familiar objects into strange new frontiers. Our solar system might seem thoroughly explored after 6 decades of spacecraft missions. Robotic emissaries have visited every planet from scorched Mercury to frozen Neptune. Landers have touched down on Venus, Mars, Titan, asteroids, and comets. Orbiters have mapped surfaces and probed atmospheres across the planetary family. The Voyager spacecraft continue transmitting from interstellar space after launching in 1977. With so much exploration already accomplished, what could remain unknown about our cosmic backyard? The answer is almost everything important. Spacecraft missions provide detailed views of specific targets during limited time windows. They cannot observe the entire solar system simultaneously or continuously monitor changes over years and decades. Ground-based telescopes offer persistent monitoring but suffer from atmospheric distortion and absorption that limit what wavelengths can be observed. Webb combines the advantages of space-based observation with infrared sensitivity and angular resolution that no previous facility could achieve. This combination reveals aspects of familiar worlds that remained invisible to every previous instrument. Jupiter's moon Europa has captivated astrobiologists for decades as perhaps the most promising location to search for extraterrestrial life within our solar system. This ice-covered world, slightly smaller than Earth's moon, orbits Jupiter every 3.5 days, locked in gravitational resonance with neighboring moons Io and Ganymede. Beneath its cracked and scarred icy surface lies a global ocean containing more liquid water than all of Earth's oceans combined. The volume of Europa's subsurface sea exceeds 2 times Earth's oceanic water inventory despite the moon's much smaller size. The ice shell provides insulation from the vacuum of space and the intense radiation environment created by Jupiter's powerful magnetic field. Charged particles trapped in that magnetic field would quickly sterilize any surface life. But organisms living beneath the ice would be protected from this bombardment. Tidal heating from Jupiter's immense gravity maintains liquid conditions in the subsurface ocean. As Europa orbits Jupiter on a slightly elliptical path, the giant planet's gravitational pull flexes the moon's interior, generating heat through friction that prevents the ocean from freezing solid. If life requires liquid water as it does on Earth, Europa represents a prime candidate for hosting biological activity beyond our planet. The ocean has likely existed for billions of years, providing ample time for any life that emerged to evolve and diversify. Hydrothermal vents on the ocean floor might provide chemical energy and nutrients similar to the deep-sea vents on Earth that support thriving ecosystems completely independent of sunlight. The basic requirements for life as we understand it all appear present on Europa, but liquid water alone cannot support life. Biological processes require chemistry far more complex than simple hydrogen and oxygen bonds. Carbon forms the backbone of all known living molecules, from simple sugars to complex proteins and the genetic material DNA. Nitrogen enables protein construction through amino acids. Sulfur and phosphorus participate in essential metabolic reactions that transfer energy within cells. Without these elements available in appropriate chemical forms, life cannot emerge regardless of how much liquid water exists. Understanding whether Europa's ocean contains the chemical ingredients necessary for life requires detecting these elements in material derived from the subsurface environment. Surface observations cannot directly sample the ocean lying beneath miles of ice, but geological processes occasionally bring oceanic material to the surface, where it can be studied remotely before radiation bombardment destroys the chemical signatures. Webb addressed this crucial question by detecting carbon dioxide concentrated on Europa's surface in patterns suggesting oceanic origin. The carbon was most abundant in a geologically young region called Tara Regio, a zone of disrupted terrain, sometimes called chaos terrain, where the ice shell has been broken and reformed relatively recently. This spatial correlation between carbon dioxide concentration and recent geological activity suggests that carbon-bearing material from the ocean reached the surface through processes that disrupted the ice and has not yet been destroyed by the radiation bombardment that gradually alters exposed surface chemistry over millions of years. The discovery carries profound implications for Europa's habitability. Carbon is not merely present on Europa's surface. It exists in forms and locations consistent with derivation from the subsurface ocean rather than delivery by external impactors or production through radiation chemistry. The ocean apparently contains carbon compounds available for potential biological chemistry. Combined with previous detections of water, various salts, and other compounds, the emerging picture suggests that Europa's ocean possesses chemical complexity potentially sufficient for life to emerge and thrive if conditions allow. Future missions will directly investigate Europa's habitability through close-range observations and measurements impossible from Earth or near-Earth space. NASA's Europa Clipper spacecraft launched in October 2024 and will arrive at Jupiter in 2030 after a long journey through the inner solar system. The mission will perform dozens of close flybys analyzing Europa's surface composition, ice shell structure, potential plume activity, and interior properties through gravity measurements. The European Space Agency's JUICE mission launched in 2023 and will also study Europa during its tour of Jupiter's moons before entering orbit around Ganymede. Webb's detection of oceanic carbon demonstrates that chemical conditions on Europa merit this intensive investigation and helps guide what future missions should seek. Saturn's moon Enceladus provided even more spectacular evidence for active ocean chemistry that exceeded all expectations based on previous observations. This small world, measuring only 300 miles across, was considered geologically dead before the Cassini spacecraft arrived at Saturn in 2004. Initial expectations suggested a frozen ice ball too small to retain internal heat. What Cassini discovered transformed Enceladus into one of the most scientifically compelling objects in the solar system. Dramatic geysers erupt through cracks in the moon's icy surface in a region near the South Pole called the Tiger Stripes because of their distinctive parallel appearance. These geysers spray water vapor and ice particles directly into space, creating a continuous fountain that contributes material to Saturn's diffuse E-ring. The plumes originate from a subsurface liquid water ocean, maintained by tidal heating similar to Europa's ocean, but on a smaller scale. Cassini flew through these plumes multiple times, directly sampling material ejected from beneath the ice. The spacecraft detected not just water but complex organic molecules, molecular hydrogen, and other compounds, suggesting active chemistry in the subsurface ocean. The hydrogen detection was particularly significant because it indicates ongoing hydrothermal reactions between water and rock on the ocean floor. Such reactions provide chemical energy that could potentially support life forms similar to the chemosynthetic organisms thriving around hydrothermal vents in Earth's deep oceans. Enceladus appeared to possess all the basic ingredients for life in an accessible package that geysers continuously deliver into space. Webb observed Enceladus and detected a water vapor plume that exceeded all previous observations in both spatial extent and apparent activity level. The plume extended far beyond what Cassini had documented, indicating vigorous ongoing subsurface activity driving material ejection into space. The Moon continues actively venting its subsurface ocean, despite its small size and limited heat sources, demonstrating that tidal heating can maintain geological activity on worlds far smaller than previously thought possible. The Webb observation confirmed that Enceladus remains one of the most compelling astrobiology targets in the solar system, deserving future dedicated investigation. Its subsurface ocean contains liquid water, complex organic compounds, and chemical energy sources produced through water-rock interactions. The geyser activity provides direct access to ocean material without requiring any spacecraft to land, drill through ice, or descend into a subsurface sea. A future mission could simply fly through the plumes as Cassini did. But with more sophisticated instruments designed specifically to search for biosignatures, understanding what chemistry occurs beneath the ice could reveal whether conditions suitable for life exist on this small frozen moon, or whether some missing ingredient prevents biology from emerging. Webb turned its powerful infrared instruments toward the ice giants Uranus and Neptune, worlds that remain poorly characterized compared to their larger cousins. Jupiter and Saturn, despite their significant scientific importance. Only one spacecraft has ever visited these distant planets in the outer solar system. Voyager 2 flew past Uranus in January 1986 and Neptune in August 1989, providing brief glimpses during its grand tour of the outer solar system. Those flybys occurred more than 3 decades ago, and since then, these ice giants have been studied almost exclusively through Earth-based telescopes with capabilities severely limited compared to spacecraft observations. Uranus and Neptune represent a class of planet more common throughout the galaxy than any other type, based on exoplanet surveys. Worlds intermediate in size between Earth and Neptune dominate exoplanet catalogues, yet we have no local examples to study in detail except these 2 distant ice giants. Understanding Uranus and Neptune is essential for interpreting observations of the countless similar worlds orbiting other stars throughout the Milky Way. The ice giants serve as Rosetta Stones for translating sparse exoplanet data into physical understanding. Webb's infrared instruments reveal details about both ice giants that ground-based telescopes cannot detect due to atmospheric absorption and limited angular resolution. For Neptune, Webb captured the clearest view of the planet's ring system in more than 30 years since Voyager 2's flyby. Neptune possesses a faint ring system discovered from Earth through stellar occultation observations before Voyager arrived. But the rings have been extremely difficult to image from Earth-based facilities. Neptune's methane-rich atmosphere strongly absorbs infrared light at the wavelengths where Webb observes, making the planet appear remarkably dark in the resulting images. The atmospheric methane absorbs incoming sunlight and re-emits it at wavelengths outside Webb's sensitive range, leaving the planetary disk nearly black. Meanwhile, Neptune's icy rings reflect infrared radiation more efficiently than the atmosphere absorbs it, appearing as bright structures encircling the darkened planetary disk. This contrast reversal compared to visible light images creates a striking and scientifically informative view. High-altitude clouds of methane ice also appeared as bright streaks against Neptune's dark atmospheric background. These clouds form when atmospheric circulation carries methane gas to altitudes where temperatures drop low enough for condensation into ice crystals. The clouds trace wind patterns and atmospheric dynamics impossible to study through other observational techniques. Webb's observations revealed cloud activity and distribution patterns that complement decades of ground-based monitoring, providing calibration points that help interpret the long-term observational record. Most remarkably, Webb detected auroras on Neptune for the first time in observational history. Auroras occur when charged particles from the solar wind become trapped in a planet's magnetic field and spiral along magnetic field lines toward the poles. When these energetic particles strike atmospheric molecules, the collisions transfer energy that the molecules release as light, producing the glowing displays visible at high latitudes on Earth during geomagnetic storms. Neptune possesses a complex magnetic field tilted and offset from the planet's rotation axis, creating conditions where auroras should occur. But despite theoretical predictions, Neptune's auroras had never been directly observed until Webb's infrared sensors captured their faint emission for the first time. Uranus observations proved equally productive in revealing new aspects of this strange tilted world. Uranus rotates on its side with its axis pointed nearly at the Sun, creating extreme seasonal variations where each pole experiences decades of continuous sunlight, followed by decades of continuous darkness. Webb captured the planet's ring system with unprecedented clarity, resolving structural details that ground-based observations cannot achieve. The telescope also imaged 9 of Uranus's 27 known moons in a single observation, demonstrating its ability to characterize the entire Uranian system simultaneously. Uranian rings are dramatically darker and narrower than Saturn's famous bright ice rings, making them extremely challenging targets for astronomical imaging. Where Saturn's rings shine brilliantly with reflected sunlight, Uranus's rings absorb most incident light and reflect very little back toward observers. Webb's infrared sensitivity and freedom from atmospheric distortion enabled clear detection of these subtle structures orbiting the tilted ice giant. Beyond characterizing known features, Webb discovered a previously unknown moon orbiting Uranus that had escaped detection through decades of observations. This tiny satellite joins the growing census of Uranian moons, expanding the planet's known satellite count from 27 to 28. Small irregular moons like this newly discovered object were likely captured from the population of small bodies in the outer solar system, rather than forming in place around Uranus from the same material that built the planet. Each discovery of such captured moons adds to understanding of how gravitational interactions shaped the outer solar system and redistributed small bodies among the giant planets. Saturn received detailed Webb attention, despite having been extensively characterized by the Cassini mission that orbited the ringed planet for 13 years between 2004 and 2017. Cassini's instruments operated at wavelengths different from Webb's infrared capabilities, meaning the Space Telescope could reveal complementary information about atmospheric composition and ring structure that Cassini could not access. At the specific infrared wavelength where Webb observed Saturn, methane gas in the planet's atmosphere absorbs most incoming sunlight extremely efficiently. This absorption makes Saturn's disk appear extraordinarily dark compared to familiar visible light images that show the planet's characteristic butterscotch coloration from ammonia clouds. Meanwhile, Saturn's water ice rings reflect infrared radiation efficiently at these same wavelengths, appearing as brilliant structures encircling the darkened planetary disk in dramatic contrast. The visual effect creates a striking appearance, unlike any previous Saturn image, with bright rings surrounding an almost invisible planet. 3 of Saturn's moons appeared as bright pinpoints alongside the ring system in Webb's observations. Titan, Enceladus, and other satellites visible in the field demonstrated Webb's ability to study the entire Saturnian system in single pointings. The observations establish baseline measurements that future monitoring can compare against to track seasonal changes in Saturn's atmosphere as the planet progresses through its 29-year orbital period. Even extensively studied worlds reveal new secrets when observed at wavelengths that previous instruments could not access effectively. Jupiter displayed atmospheric phenomena never previously observed when Webb examined the solar system's largest planet. The telescope revealed a narrow jet stream traveling at speeds exceeding 320 miles per hour, located directly above Jupiter's equator, at altitudes above the main visible cloud deck. This high-speed wind current sits above the cloud layers, visible in optical images, demonstrating that Jupiter's atmosphere contains distinct layers with different circulation patterns that interact in complex ways scientists are still working to understand. The newly detected jet stream appears narrow compared to the broader banded wind patterns visible at lower altitudes in Jupiter's atmosphere. Understanding how these different atmospheric layers interact and exchange energy and momentum helps explain Jupiter's global circulation and the persistence of features like the famous banded appearance that has characterized the planet for centuries of telescopic observation. Understanding atmospheric dynamics on Jupiter helps interpret observations of giant exoplanets orbiting distant stars throughout the galaxy. Jupiter serves as a natural laboratory where atmospheric processes can be studied in exquisite detail that distant worlds simply do not permit given current technology. The physics governing cloud formation, wind patterns, storm development, and chemical cycling in Jupiter's atmosphere applies equally to the countless giant planets Webb observes in other stellar systems. Lessons learned from Jovian meteorology through close-range observation directly inform models used to interpret sparse exoplanet data. Webb also captured new features above Jupiter's famous Great Red Spot that optical observations cannot reveal. This enormous storm, larger than Earth, has raged continuously for at least several centuries, persisting through atmospheric dynamics that scientists do not yet fully understand. What sustains this colossal vortex, while smaller storms form and dissipate within years, remains mysterious, despite decades of observation by spacecraft and telescopes. Infrared observations reveal aspects of the storm structure that visible light cannot detect, including thermal variations, chemical distributions, and altitude information throughout the feature's enormous extent. These observations will help constrain models seeking to explain the Great Red Spot's remarkable longevity. Saturn's mysterious moon Titan received sustained Webb attention as one of the most scientifically compelling worlds in the outer solar system for understanding prebiotic chemistry. Titan is unique among all solar system moons in possessing a dense, substantial atmosphere. Surface pressure on Titan exceeds Earth's sea level pressure by roughly 50%, creating an environment where liquids can exist stably on the surface, rather than immediately evaporating into vacuum as they would on airless moons. Complex organic chemistry in Titan's nitrogen-dominated atmosphere produces hydrocarbon haze that completely obscures the surface from optical observation. Sunlight drives reactions that build simple atmospheric molecules into increasingly complex organic compounds that eventually grow heavy enough to settle onto the surface. This continuous rain of organic material coats Titan's surface with complex chemistry that may resemble conditions existing on early Earth before life emerged. Titan's surface hosts features utterly unlike anything elsewhere in the solar system. Lakes and seas of liquid methane and ethane dot the polar regions, creating the only standing bodies of liquid currently known to exist on any world besides Earth. Rivers of liquid hydrocarbons have carved channels and valleys through the terrain over geological time. Vast dune fields of organic sediment cover equatorial regions, shaped by winds into patterns resembling terrestrial sand dunes but composed of entirely different materials. Webb's infrared instruments can penetrate Titan's atmospheric haze at specific wavelengths, where the haze becomes transparent, enabling direct observation of surface features and atmospheric phenomena. Observations revealed clouds forming over Titan's northern hemisphere during late summer conditions, as that region receives increased solar heating following northern spring equinox. The clouds appeared to evolve between sequential Webb observations and additional follow-up measurements from large ground-based telescopes, demonstrating active meteorological processes on this distant frigid world. Webb contributed to planetary defense efforts by observing asteroid 2024 YR4, an object that briefly attracted worldwide attention as a potential Earth impactor. Initial orbital calculations based on limited observations suggested a small but non-negligible probability that this asteroid might strike Earth in the late 2025 to early 2032 timeframe. Such announcements trigger intensive observation campaigns to refine orbital predictions and determine whether impact scenarios remain viable or can be ruled out. Webb collected critical observations when the asteroid was too distant for ground-based telescopes to characterize effectively due to its faintness. The Space Telescope's sensitivity enabled measurement of the asteroid's infrared brightness, which combined with distance information allows estimation of size. Knowing the size of a potential impactor dramatically affects risk assessment since larger objects cause more damage. Webb's observations also helped refine the orbital trajectory by providing positional measurements at times when ground-based facilities could not observe. Subsequent analysis incorporating Webb's data and additional ground-based observations determined that asteroid 2024 YR4 poses no significant threat to Earth. The refined orbital solution ruled out impact scenarios that initially seemed possible based on limited data. However, the observation campaign demonstrated Webb's capability to characterize potentially hazardous objects at distances where other facilities cannot operate effectively. Understanding asteroid sizes, compositions, and precise trajectories informs impact risk assessment and mitigation planning for any future objects discovered on concerning trajectories. Webb provides a capability that may prove critical if a genuine impact threat ever materializes. Perhaps the most scientifically significant solar system observation involved a visitor from far beyond our planetary system entirely. In late 2025, Webb observed Comet 3I Atlas, only the third confirmed interstellar object ever detected passing through our solar system. Unlike comets that formed in the cold outer reaches of our solar system from material left over after the Sun and planets assembled, interstellar comets originated around other stars entirely. Gravitational interactions in their home systems ejected them into deep interstellar space, where they wandered for billions of years before chance brought them close enough to our Sun for detection. Previous interstellar objects had been detected only briefly before departing the inner solar system on their hyperbolic trajectories back into interstellar space. The first confirmed interstellar object, designated 1I Oumuamua and detected in October 2017, displayed highly unusual properties that generated substantial scientific debate about its true nature. Its elongated shape, lack of visible cometary activity despite passing close to the Sun, and apparent non-gravitational acceleration led some researchers to speculate about exotic origins, while others proposed natural explanations involving unusual composition or structure. The second interstellar object, 2I Borisov, discovered in August 2019, appeared much more clearly cometary with a visible coma and tail similar to ordinary solar system comets. But it too was observed for only limited duration as it passed through and departed. Both objects were discovered after they had already made their closest approaches, limiting observation time before they receded beyond detection capability. Comet 3I Atlas provided more extended observation opportunities that Webb exploited for detailed spectroscopic characterization, revealing the chemical composition of material formed in another stellar system entirely. Webb's infrared spectrograph decomposed light from the comet into constituent wavelengths, identifying absorption and emission features from specific molecules. This molecular inventory reveals what compounds exist in the comet, and by extension what materials were present in the protoplanetary disk where it formed billions of years ago. The comet displayed characteristics differing from typical solar system comets, including unusual ratios among various molecular species detected in its coma. These compositional differences likely reflect the distinct conditions that prevailed in whatever distant stellar system birthed this interstellar wanderer. Different stars form from gas clouds with different chemical compositions. The protoplanetary disks around those stars inherit and modify those compositions through physical and chemical processes. Comets preserve samples of disk material that planets subsequently incorporated, or that remained frozen in the outer reaches of planetary systems. Interstellar objects provide direct samples of extrasolar material delivered to our doorstep without requiring interstellar travel. Each object carries information about the planetary system where it formed, the chemical and physical conditions that prevailed during its formation epoch, and the dynamical processes that eventually ejected it into galactic wandering. Studying these rare visitors complements exoplanet observations by revealing what solid materials exist around other stars. Webb's characterization of 3I Atlas adds to the slowly growing database of interstellar object properties that future detections will expand. The solar system discoveries across all these diverse targets demonstrate how much remains genuinely unknown about our immediate cosmic neighborhood, despite decades of planetary exploration. Moons with subsurface oceans containing organic chemistry that might support life, giant planets with atmospheric dynamics, operating through mechanisms we are only beginning to understand despite centuries of observation. Ice giants so distant that spacecraft have visited them only once during brief flybys more than 3 decades ago. Visitors from other star systems passing through on trajectories that will never return, offering glimpses of distant stellar environments. Webb provides capabilities that extend and transform decades of planetary exploration, revealing the familiar planets and moons in wavelengths and detail that fundamentally change understanding. Features invisible to previous instruments now stand revealed. Processes operating beneath surfaces or in upper atmospheres become accessible to study. Compositions and chemistries, hidden from optical observation, emerge under infrared scrutiny. These local observations connect intimately to broader themes pervading all of Webb's science across cosmic distances. Understanding subsurface ocean chemistry on Europa and Enceladus illuminates how liquid water environments might exist on icy worlds throughout the galaxy, informing habitability assessments for countless exomoons. Characterizing atmospheric dynamics on Jupiter and Saturn helps interpret the sparse observations possible for giant exoplanets orbiting distant stars. Studying comets and asteroids reveals the building blocks from which all planetary systems assembled and shows how those materials distribute through dynamical evolution. The solar system serves as a laboratory where the processes shaping worlds everywhere in the universe can be studied in matchless detail, impossible for any distant target. We can send spacecraft to solar system objects. We can observe them continuously across decades. We can study them at wavelengths absorbed by interstellar medium before reaching distant sources. Everything we learn about solar system worlds calibrates and informs interpretation of observations throughout the cosmos. Webb has peered across billions of light years to cosmic dawn when the first galaxies assembled from primordial gas. It has examined worlds orbiting our own sun at distances measured in hundreds of millions of miles rather than trillions. In both realms, spanning the extremes of accessible cosmic distance, the telescope has found phenomena that challenge understanding and reveal how much remains to be discovered regardless of where we look. Galaxies assembled faster than models permitted. Black holes grew beyond theoretical limits. Exoplanet atmospheres behave in ways predictions completely failed to anticipate. Nearby moons harbor chemistry that might prove favorable for life. The universe Webb reveals is stranger and richer than previous generations could have imagined with their more limited observational tools. Every observation challenges some assumption that seemed secure. Every discovery raises new questions that previous frameworks cannot answer. The telescope continues accumulating data that will reshape cosmic understanding for decades to come, as researchers analyze, debate, and synthesize what the observations mean. Scientists will argue about interpretations of ambiguous results. Models will be revised or abandoned entirely when observations prove them inadequate. New theoretical frameworks will emerge to explain what we observe, only to face their own tests as further observations probe their predictions. This iterative process of observation, interpretation, revision, and further observation constitutes the engine driving scientific progress across all fields. The universe is not what we thought it was before Webb launched. It is bigger than old estimates suggested, stranger than conventional models predicted, more ancient in its massive structures than formation theories allowed, more alive with possibility for habitable environments than pessimistic assessments assumed. Webb has demonstrated that everything we think we know remains genuinely provisional, always subject to revision when better observations become available and challenge comfortable assumptions. That uncertainty represents not weakness in scientific knowledge, but rather its greatest strength. We follow evidence wherever it leads, even when destinations prove surprising and require abandoning ideas that seemed well established. The willingness to revise understanding when observations demand it distinguishes science from dogma. Webb provides observations that demand revision across multiple domains of cosmic understanding simultaneously. The James Webb Space Telescope looked deep into the unknown, across scales ranging from our neighbouring moons to the edge of observable space. What it found has proven genuinely shocking in the original meaning of that overused word. The shock comes not from discovering a hostile or meaningless cosmos that renders human existence absurd. It comes from finding a universe far more complex, more dynamic, and more full of wonders than human imagination managed to anticipate. We are small creatures, living brief lives on a small world, orbiting an ordinary star in the outskirts of an ordinary galaxy. Yet we have built instruments that see to the edge of observable space and the beginning of cosmic time. The secrets those instruments have found only deepen the mystery of existence itself, inviting continued exploration of a cosmos that refuses to stop surprising us. No matter where we look, or how carefully we observe,